Super Young-Mills, yes. Yes, thanks for the introduction, and I'm glad that all of you made it after the nice treatment yesterday evening. And after these 2 sets of talks, I should all invite you to free coffee outside, so you can also wake up. So this talk is about Yangian symmetry and integrability of planar n equals 4 super Young-Mills theory, and I've been recently told by physrefd to always spell out what abbreviations mean, and so that's perhaps a useful thing, at least for this one. And this is work in collaboration with 2 students, one former student, Matteo, and a current student, Alexander, who's finishing up. And the aim of these projects is basically to prove Yangian symmetry in integrable planar gauge theories, where n equals 4 super Young-Mills is certainly the most prominent example of. And the outline of this talk will be that I first tell you what, in what sense we can understand the Yangian algebra as a symmetry of the planar sector of n equals 4 super Young-Mills or related gauge theories. And then in perhaps the second part of the talk, I will tell you what implications this may have for the quantum field theory. For example, what these symmetries mean for correlation functions, and maybe if I have time, I can also outline you some aspects of the Yangian algebra and how they involve the gauge transformations. But that depends a bit on the time. Okay, so the general assumptions in this talk will be that I will be talking about n equals 4 supersymmetric Young-Mills theory. I will also introduce some of the relevant aspects of it later on. And I will certainly be interested only in the planar limit. That is when the rank of the gauge group becomes very large. And well, in fact, most of the results that I present also apply to different planar gauge theories, and the other main example is ABJM theory. Yes, ABJM, I was also told by physrefd to spell it out. It's the authors of the article, but it's just known as ABJM theory largely. And more down-to-earth description of what this means is n equals 6 supersymmetric Chern-Simons theory in 3 dimensions coupled to some matter. But yeah, this is Aharoni, Bergman, I believe, Jaferes and Malesina. Okay, so let me start by introducing or telling you about Yangian symmetry of this gauge theory, and well, this all started with integrability of planar n equals 4 super Young-Mills, and later on some related gauge theories such as ABJM. And Kostya yesterday has given a useful introduction to some of these features. Also, Volodya has introduced integrability in this model, and they've shown you some methods to make use of integrability to perform some efficient computations of some observables. And that's basically how this topic of integrability in equals 4 super Young-Mills has been used throughout the last 15 years or so. So prominent examples are that the planar spectrum of anomalous dimensions has been determined through integrable methods, not just perturbatively, but even by solving some integral equations at finite lambda. And more recent applications is that correlation functions of local operators are being computed well, rather efficiently. And another context is color-ordered scattering amplitudes. This is certainly also interesting because scattering amplitudes are very hard to compute, especially at loop level. And so if you can use integrability to make some determinations, you can get further, and people have gotten quite far with determining scattering amplitudes, loop integrals, or at least loop integrands for integrability. A related topic is null polygonal Wilson loops. And in particular, as I said, the loop integrals should be computable by means of integrability, but so far people have mostly investigated loop integrands and determined them through methods which are somewhat related to integrability. But one question that is left open by all of these applications is what precisely is this integrability? And that's an essential thing you have to answer before you can prove that this model is integrable in the first place. I mean, these methods all rely on integrability, but and they have been shown to work well by comparing them to explicit computations. But and there have been proofs for certain parts of these methods, but there was no really a general proof what this integrability in n equals 4 or well, that it applies to everything in n equals 4 super Yang-Mills. Yeah. The point of view I will be taking is that integrability is a symmetry enhancement. It's some hidden symmetry that is there in the planar limit of this theory, and more concretely, it enhances the space-time symmetries, which here are the conformal or the superconformal symmetries, which go by the Lie algebra, superalgebra PSU 2.2/4, and extend that to an infinite-dimensional Yangian algebra, quantum algebra, based on this superconformal algebra. So the question is, in what sense is the Yangian actually a symmetry? Well, if you look at, for example, all of these applications, the Yangian has mostly not really been a symmetry. For example, the spectrum is not invariant. For example, well, that's because the boundary conditions in this integral problem actually destroy the symmetry. Scattering amplitudes are almost symmetric, but you get IR divergences due to massless particles, and they somehow distort the symmetry. For Wilson loops on null polygons, you get UV divergences instead, and they also mess around with the symmetries. There are, in fact, some class of observables which are smooth Mulder-Sehner-Wilson loops, which are finite and invariant, and for those, the Yangian actually does seem to be a symmetry. But the symmetry for other observables is less evident, and the way the Yangian has usually been understood is that it's some ordering principle, some algebra that helps you construct useful states, but it's not really a symmetry. It provides you basically just the tools. But of course, if you have a symmetry, if you see this symmetry all throughout the theory, you would think that perhaps the action of this theory should be invariant. And well, this would be a natural thing to assume and prove, but there are certain complications that made it difficult. For example, the representation of this Yangian is typically nonlinear in the fields. You have cyclic boundary conditions, and this is something that usually does not go well together with a Yangian symmetry. It's not really clear how to implement the planar limit at the level of the action, because the action is something, but some object where you don't really have a planar limit, whereas the planar limit usually just restricts the Feynman diagrams that you will be looking at, and so it's not so clear how to impose the planar limit on the action. There are also some non-local properties which are not so clear how to deal with them concerning the Yangian and the action, and eventually, even if you could show that the action is classically invariant, there may still be quantum anomalies which you should consider at some point. So anyway, so let me just tell you what I mean by the Yangian. The Yangian is a quantum algebra which is defined in terms of two types of generators, or can be defined in many ways, but I will take the point of view that there is a set of level 0 and level 1 generators. The level 0 generators I call J, with some index A, where A enumerates the superconformal algebra PSU 2.2/4, and J hat is another set of these generators which are somewhat similar, but yeah, they form another set and they are independent. Now the algebra relations you can summarize in more or less like this. So so there's the Lie algebra at level 0, with the structure constants of the superconformal algebra. Then here you get the adjoint property of the level 1 generators. And then there's the so-called Serre relations, which are more complicated, which I don't really write out. But they constrain somewhat the level 1 generators. Yes? Say again? Level, it's you can also view the Yangian algebra as a loop algebra, and then level 0 would be the level 0 of the loop algebra, and level 1 would be level 1. And then there are many higher levels which you get by repeated commutators, but I don't really need to specify them. The only point about this Serre relation is that it somehow restricts the algebra, and we don't really want to look at it, and the reason is that it's complicated, but it also is not so harmful, because suppose the Serre relation would not hold, this would just make the algebra bigger and more constraining. So in that sense, it's sort of natural to believe that the Serre relation will somehow hold, even though we don't really check that. Anyway. And then this is a Hopf algebra, so you get a coproduct which you specify for level 0, which is just the ordinary tensor product rule. For level 1, you get some bilocal terms which actually make these level 1 generators in some sense bilocal, whereas the level 0 generators turn out to be local in some sense. What we usually, or for practical purposes, we just typically consider the level 0 generators which form this Lie algebra, and at least one level 1 generator, and there's a convenient one which is the level 1 momentum generator, p hat. P hat is nice because you can express it in terms of quite simple, I mean, you can express the coproduct in terms of the Poincaré generators, the super Poincaré generators, which are the momentum generator, the Lorentz rotation generator, and supersymmetries, and also the dilatation. And you don't actually need to touch the special conformal transformations, which always are a bit of a mess. And the nice thing about that is that these generators not only exist in a super conformal theory, but they also exist in many just supersymmetric theories. And so you could, in principle, generalize this definition of the level 1 momentum to other models. For example, any super Yang-Mills theories in different dimensions or with different numbers of supersymmetries. You can also define the level 1 momentum and see whether that will be a symmetry, and that therefore determine or have a criterion for which models are integrable and which models are not. But this conference here is about spin chains, and so the question is where is the spin chain? Or put differently, how to represent this Yangian symmetry algebra in n=4 super Yang-Mills. So you can view many interesting objects in n=4 super Yang-Mills as spin chains, and the spins are typically just the fields. So you have the fields, which I just collectively denote by Z, and Z may be a gauge field or a fermionic field, a spinor field, or maybe one of the scalar fields. We don't really need to care about the indices at this point, but what's important is that fields in a quantum field theory can or do depend on X, but this X dependence you could also view as being a tower of derivatives in a sense of a Taylor expansion of the field. So the different spin degrees of freedom are these different flavors and the different indices, but you can also have derivatives to create more spin degrees of freedom. So this will be an infinite dimensional representation. And another aspect that's important is that all of these fields are n by n matrices. And so what this means, well, I'll come back to this, but that's something you have to keep in mind. This is an SUN gauge theory, and all fields are n by n matrices. So how about the symmetry and the representation? Well, yes. That comes here, I hope. Yes. The capital N has I guess the rank is 8. 8 equals 4 for the conformal, 3 for the conformal algebra plus n, which is also 4. So you get close to 8. Minus 1 for the U1s that you subtract. Okay, anyway, so this PSU 2.2/4 contains the conformal algebra, and that contains the Poincare algebra. So you do have a momentum generator P, and that would act on the generic field by a derivative. As usual, you take a field to its derivative. If you already have a derivative, you would have 2 derivatives and so on. And now, so this tells you how in general this momentum generator would act. But since it's a gauge theory, you would rather not have ordinary derivatives. You would rather write things in terms of covariant derivatives, just to make things as covariant as possible. So P mu acts by taking a field to its covariant derivative, and the covariant derivative is the ordinary derivative plus a commutator with a gauge field. And that's one way of seeing why this is a nonlinear representation, because it maps one field to, well, one field or potentially 2 fields. And that's in that sense the representation is nonlinear in the fields. Similarly, the rotations would act by how rotations act, just with covariant derivatives. And supersymmetries, they do operate on these fields in a particular way. For example, they take a scalar field to a spinor field, and they would take a spinor field to the derivative of a scalar field, so that you can realize the supersymmetry algebra. And I'm not going to go through all of the generators. The only point I want to make is that you can establish a representation of the level 0 generators on these fields. That's the important point. So the other important aspect is that all fields are n by n matrices, and you can combine these matrices to monomials. You can take products of matrices, and if you take such a product, you'll get back a matrix. And this monomial is again an n by n covariant matrix. And importantly, the ordering of these fields matters. If you have n sufficiently large, at least, then all of these polynomials will be independent. And the monomials of different length can also be mixed. So if you have they're both are capital, but one. Oh, that one. This n can be any number, any integer. No. Capital N is large. This is the planar limit. This is the rank of the gauge group. Yes. Yes, and that's the nice thing. This is not normally, but this is n equals 4 super Young-Mills, and it's special. But I mean, the length n is not, this length of the spin chain is not going to be infinite. Typically, we have a finite n, but more importantly, the n is not even a fixed number. It's because you mix different fields. For example, for a covariant derivative, you mix, say, a single derivative of a field with this commutator of 2 fields. So in that sense, if you translate it to these things, then monomials of a given degree are not interesting, but what's more interesting is actually polynomials of variable length. All spin chains of different length can mix. They form, the Hilbert space is sort of, for this spin chain, contains spin chains of arbitrary length. But typically they are finite. So you sort of have spin chain states of variable length. Such polynomials will be relevant for various objects that you encounter in QFT. So for example, local operators, that's how this enterprise of integrability in X4 super Young-Mills started, where you take a trace of such a polynomial here. That will be a local operator if all of these fields are evaluated at the same point in space-time. Another interesting class of observables are Wilson lines. These are path-ordered exponentials of the gauge fields along a certain path. And these are similarly well, if you take Wilson lines or Wilson loops, they are similar to local operators, but they are just not local, so they are some sense non-local operators. You can also look at color-ordered correlators, where you take several fields at several different space-time points and evaluate their quantum correlation function. So these will be some functions which depend on positions and also on the various flavor indices of the fields. And finally, the action is also such a local operator. It's actually an the integral of the Lagrangian, and the Lagrangian is something like f mu nu plus other terms, whichever you need for this theory. But that's also something which you can express as such a field polynomial. Okay, now how does the Yangian act on such polynomials, or on the spin chains that we are interested in here? So first, level 0 is an ordinary Lie symmetry, and that acts by more or less by a tensor product. So when you act on such a monomial, you would act on all of these letters in the monomial by just mapping each field to its transformed field. The only thing you have to pay attention to is that this is potentially, this is a nonlinear action, so this may change one field to two fields. It may also take one field to one field, and just, you know, if you act on a monomial, you may end up with a polynomial of different length, non-uniform length. Okay, now, but this is how ordinary symmetries act in a quantum field theory. However, there's now also this Yangian extension, the level 1 generators, and this follows the coproduct rule, how to act on such a spin chain state. So since it's a bilocal action, you would typically have two insertions at two different points of this chain, and each of them can be linear or nonlinear, and each of them is governed by the level 0 symmetries, and you somehow contract them by the structure constants. And that's how the Yangian usually acts on spin chains, except that we have a slightly different extended notion of spin chain here. And then there can also be some local contributions, and you can view them, on the one hand you could view them as some sort of completion of the bilocal terms. Suppose these bilocal terms come very close, then if you move them even closer, they would overlap, and this would somehow be the regularization of what happens for this coincident limit. And as I said, these terms and these terms have nonlinear contributions, which makes the problem quite difficult. Okay, now if we want to act with a level 1 generator on the action of the theory, that needs extra care, mainly due to cyclicity. And so let's just consider something else instead for the time being, namely the equations of motion. And if we want to have a symmetry of a theory, then the equations of motion should be symmetric. And they should be symmetric in the sense that when you act on the equation of motion as in, well, x, let's say the equation of motion is x equals 0. So if I act with j hat on x, I should get something which is again proportional to the equations of motion. It doesn't have to be straight 0, it can also be something that is 0 on shell. But the point is really that the equations of motion need to be mapped to themselves. Now, you have several equations of motion because you have several fields, but let's look at the Dirac equation because that's easiest. The Dirac equation is something like d slash on the fermion plus a commutator with a scalar field in this particular theory equals 0. And if I spell this out, then that's an ordinary derivative plus this gauge field commutator with a field plus a commutator with a scalar field. So it's not a very difficult equation, and we can apply this p hat using this rule that we had here, and use the coproduct. So the coproduct gives you local and bilocal terms. I'm just going to summarize these bilocal terms using Sweetless notation, where J1 and J2 are the two components, and I do some intrinsic sum over various combinations. So when you do this, then, well, this term is actually linear in the field, so a bilocal term cannot act on it, but bilocal terms can act on these quadratic polynomials of the fields. and they give you these two terms, this one and that one from these two. And the interesting thing is it actually turns a commutator into an anticommutator, and that's because the bilocal term is antisymmetric, so it turns something which is already antisymmetric into something which is symmetric. So these are the bilocal terms. They are completely determined in terms of the level 0 generators, and then there are some additional terms. So these are local actions of p hat, and the point about them is that we don't really know what p hat on the fermion and on the gauge field and so on is. But by trying to satisfy this equation and other invariance conditions, we can find out what is p hat, and it's not so difficult to enumerate what p hat could possibly be by just looking at the quantum numbers. So p hat on a gauge field would give you a anticommutator of scalar fields and so on. And if you substitute the right coefficients and the right combinations here, you'll actually get 0. So in that sense, all terms cancel properly, and the Dirac equation is Yangian invariant in this sense. Okay, so that gives us some confidence that this theory as a whole is Yangian invariant, and then we wanted to show that the action is invariant. So j hat on S, which is the action, hopefully is also 0. And well, there are some essential features of the action that you need for this to be possibly true. Well, first of all, it has the right kind of topology. It's a single trace operator. The action itself is conformal. The action itself is finite, which means that you sort of have the right large N topology. The level 0 generators already annihilated, and well, if it's finite, maybe then there will be no anomalies. But a problem is that it's cyclic. It's also integrated, so it's the integral of a Lagrangian, and it's a non-homogeneous polynomial, and that all of these features are a bit difficult to reconcile with the Yangian symmetry, in particular the nonlinear aspects of the symmetry, the bilocal representation, and cyclicity. To realize all of these properties at the same time for the Yangian is difficult. But we did find a proper definition for j hat acting on S, such that j hat on S is indeed 0 when you do it in n equals 4 super Yang-Mills and other integrable planar gauge theories that we know, well, that we think are integrable, and in such a way that j hat on S is not 0 for non-integrable models. For example, you could look at n equals 4 and less than 4 super Yang-Mills in 4 dimensions, or maybe even other supersymmetric gauge theories in other dimensions. They would typically not be invariant. But the difficulty in that is if you actually act with, say, p hat on the action, you get, depending on how you count, you get up to thousands of terms, and you have to show that they actually all cancel, and they need to cancel modulo cyclic permutations and modulo integrations, that is modulo integration by parts and so on. But for n equals 4 super Yang-Mills, we showed this explicitly, that all of these terms cancel, and that all of this makes us think that this is actually a proper definition of integrability for n equals 4 super Yang-Mills and other planar gauge theory models. Yes? For large n, where n is the rank of the gauge group. Yeah, that's the usual question. Let me see if I come. No. I mean, the main reason at this stage is that if you look at polynomials of the fields, and these fields are n by n matrices, and n is not too large, then there may be identities between the different polynomials. And somehow this notion of having field polynomials is something that works best at large n. At this stage, this is the only point, and later when I come to correlation functions, there may be different reasons, but this is the best thing I can say at the moment. But let me be a bit more specific. So how do we define this j hat on S? Well, the action is first of all a polynomial of different degrees, and it may be useful to split the different degrees. And for any polynomials, you have a quadratic term, a cubic term, and a quartic term. Actually, so there are only 3 different terms here, but you can expand the action in polynomials of definite degree. Yes. Well, in this case, this is the finite sum because you have finitely many terms. Then a symmetry generator will also be expanded in how nonlinear it is. So a symmetry will start out with a linear contribution that maps a field to a field, and that would be J0, and then there's J1, which maps one field to 2 fields, and J2, which maps one field to 3 fields, and so on. In fact, there will typically just be contributions of linear and one term J1, but not. So in that sense, this is also a finite sum. And when you act with such a symmetry, such an ordinary symmetry on the action, you can again expand this action in terms of degrees, and this is an expression you would get. So somehow you would sum over all degrees of j and all degrees of s, and you need to show that all polynomials of equal degree will then cancel to make this a symmetry. Oh, comma 1 in this sense means, well, the action is a cyclic polynomial, and if it's cyclic, it doesn't actually matter on which side you act. If you act just on the first side, but n times on the first side, then this is the same as acting on all of the n sides and then using cyclic permutations to shift things back. So Jm1 means you act on the first side. That's all you need here for cyclic, for the cyclic action. Now, the problem here is for the Yangian is that you have a nonlinear bilocal cyclic representation, and typically when you act with the Yangian on something cyclic, it doesn't work. It somehow gives you something non-cyclic, but that would be bad because you still have this trace, and somehow it doesn't make sense. So that would be the definition how we act. And so there are 2 types of terms where the 2 individual generators act on 2 distinct sides, and then there's a certain prefactor which you need to make things cyclic. And then there are other terms where the 2 insertions of the level 0 generators actually overlap, because now you have the first thing which acts, and then the second generator can act on one of the legs that comes out of the first. And then, of course, there are also the local contributions. And there's one useful thing you can compare it to, namely if you act twice with the local generator. If you act twice with the local generator, then the first one will hit somewhere and the second one will hit somewhere else. So it's again a bilocal thing. And if you compare these 2, you get also similar terms. These are the terms where the 2 actions are distinct, and these are the 2 where the 2 are overlapping. And the main difference sits here in the prefactor, and the prefactor is a bit odd, and the prefactor also makes calculations very difficult, because then you have to deal with some rational numbers, and if you compare certain things, it may be that these rational numbers never match up, because the denominator is not quite what you expect. But the nice thing about this expression is that it does actually leave n equals 4 superpolynomials action invariant. So there's a certain justification for it. But it's a very funny object in terms of representation theory. Anyway, I can also show you a more elegant proof of integrability in terms of some sort of classical anomaly terms. If I say p hat acting on the action is something which I call A, and I want to check whether this A is 0, I can also consider the algebra. So the algebra says that the level 1 generator should transform in the adjoint of level 0. And so in the sense that these A mu terms should also respect the representation theory of, should respect this relation more or less. So this means that when I act with P on the anomaly or with the supersymmetry on the anomaly, I should get 0, because that follows from the algebra. And that means that this A is a vector of dimension 1. Dimension 1 I didn't show, but it's a vector object. It's translation invariant. This is something else. So A is also a vector because it carries a vector index, basically. And it's something of dimension 1 because P hat is something of dimension 1 and the action is invariant under level 0. So this is just classifying what this A should be in terms of representations. And then you can look at whether such an object exists. Now, if you say A is translation invariant, then it's probably the integral of a local operator. And this local operator should now be a dimension 5 operator because you have this dimension 4 integral measure here. And it should be the top component of a supermultiplet. This is what this statement tells you. However, here you have n equals 4 super-Mills and PSU 2.2/4 superconformal algebra. And the top components of long multiplets, there are two different types of multiplets. There are long ordinary multiplets, which are very long, and they're the top components, which are supersymmetric, those are at dimension at least 10, which means that a dimension 5 vector cannot be the top component of such a long multiplet. And then you can look at short supermultiplets, but there are actually no short supermultiplets which could give rise to such an operator, and that means classically there cannot be any anomaly. This thing simply doesn't exist, and therefore it has to be 0. There's nothing that transforms in this way by using the fields of n equals 4 super-Mills. There's even a better proof, which I'll skip. But then we can go on to the quantum theory, and well, since we've shown the Yangian symmetry of the classical action, what does this mean for the quantum field theory? Normally in a quantum field theory, a symmetry gives you conserved currents and conserved charges, but the problem here is that this is not really a local symmetry, it's a bilocal type of representation, and then it's not so clear what a Noether current or charge should be. But in a QFT, you can consider correlators of fields. So let's consider these objects. You have several fields and at different space-time points, and this gives you the set of correlation functions. And if you have a symmetry, then these would typically obey some Ward or Ward-Takahashi type identities, which you can actually formulate where you say, well, for level 0, for the conformal symmetries, you would transform each of these fields individually and say that the expectation value of that would be 0. That's how Ward identities work ordinarily. Now, for the level 1 generators, you have this bilocal terms, and then, but since this is again some sort of field polynomials, you would just insert two different level 0 generators at two different positions, and then sum over their insertion points and so on. So this just follows the same coproduct rule we had earlier. And the hope would then be that if J hat is a symmetry of the action, this would translate to a Ward identity that this correlation function here is exactly 0. The complication for n equals 4 super-Mills is that it's a gauge theory. So in principle, you should do gauge fixing before you can do any of before you can compute any correlator. You do have in gauge fixing, you typically have some unphysical degrees of freedom, and you have to say how the Yangian would act on those. And another complication is that the Yangian closes only onto gauge transformations. So in that sense, we should consider the Yangian algebra and also the gauge transformations. But in view of time, I will skip that. So let's just go to the last aspect. So let's say we have fixed the gauge. We have settled how to deal with gauge fixing in connection with the Yangian symmetry, and address your question first. Yes. Yeah, it adds the complications. Yes. Yes. Yeah. Yes, yes. Well, I don't know how to best answer this question. Well, I use the covariant derivative to explain you this problem of nonlinear effects, but the nonlinear effects would be there anyway because it's an interacting quantum field theory, so you will have to deal with this in some way anyway. Now, in a gauge theory, I would say it's not very wise to mess with the gauge structures too much. If the way to properly mess the gauge theory is to gauge fix it with one of the known methods, such as BRST or Falev-Popov type gauge fixing, and then understand the algebraic aspects of that, and that's what we did. And then we see that the gauge fixing is actually compatible with the Yangian symmetry, but it makes things more complicated. Now, yeah, maybe I can address your question later on. Let me just go on with the correlation functions. So here I say, well, let's assume this is not a gauge theory, that gauge fixing is not a problem, and let's just see how Yangian symmetry acts on correlators of fields. Yes, no. Okay, so here I want to show you some correlation functions that appear in n equals 4 super Yang-Mills. The easiest would be the propagator. So you do have two different spacetime points, and Z1 and Z2. This is not gauge invariant, but since we do gauge fixing, it doesn't matter. We know how to deal with it. Then a three-point correlator would yield such a diagram here. You have three external points, and they would be connected by a cubic vertex. And then this may be interesting because for four fields, you can get this quartic vertex, but you can also get two cubic vertices connected by an internal line. And that's maybe interesting because we have to understand how the Yangian acts on these internal lines later on. And then we can also look at loop effects, and the first interesting loop effect will be for the one loop correction to this, and that gives three types of diagrams, such a thing where you have a full three-point internal loop, but also some other internal loops. I will always restrict to planar and color-ordered contributions, and this will also be fully off-shell in the sense that these are three generic points in space-time, and so you first have to connect them by some propagator, which is not on-shell, to some central vertices. So what, how do you see the symmetry, for example, for the propagator? Now the propagator is very simple, and I can actually prove why this is symmetric under the Yangian. But let's see first how it acts. When you act on a correlator of two gauge fields, what you get is the two superconformal generators acting on the first leg and on the second leg, contracted by the structure constants. And the claim is that this particular correlator gives you something which is a double total derivative with respect to the first and the second point. This again relates to the gauge theory nature of this theory, because this doesn't really have to be zero. All we have to show is that this has to be a gauge transformation, and that somehow tells you it's a gauge transformation. The point is that whenever you act on gauge fields, these things don't have to be exactly symmetric, but they only have to be invariant up to a gauge transformation, which is a covariant derivative. Anyway, so I want to show this statement, and instead I can look at acting with the derivative on the first field to make this a field strength, and then when I do that, then I get this correlator where one of the fields has become a gauge. It's some function which, yeah, some function. Some particular remainder function. It doesn't really have much of a relevance. Yeah, but this means since you have derivatives here, this means up to gauge transformations. No, I mean this is this is an infinitesimal variation. So if you vary the correlator, you should get 0. This is almost 0. This is as good as 0 in a gauge theory. So what you can do is when you look at this correlator here, you can take one of the two generators and pull it out of the correlator so that you make it act on anything. This is something like integration by parts, if you wish. So you have this JA acting on this, and then there's that. Now the point is that this is now a correlator which is gauge invariant, and as such it should be, the variation of it should be 0. So in that sense this term should be 0 just by level 0 symmetry. And the other term here is 0 because JAJB contracted with the structure constants is the commutator, and this eventually gives you this combination which gives you the dual Coxeter number of the model, and that's 0. So for some combination of nice facts, this thing is 0, and if this is 0, then you can show that this thing should actually be a double total derivative. Okay, so that's well, a napkin version of the proof for the Yangian symmetry of the propagator. But the propagator is in some sense too easy. And let's look at now 3-point functions. How does this work? If you want to show the symmetry, let's just start with the level 0 generator, because that's something where we know this should be 0. So then when you act on such a correlator, you insert a linear transformation on each of the 3 legs. But you can also act with a nonlinear contribution, and this takes one field to 2 fields, so it turns this one field to 2 fields, which can then be connected to the other 2 external legs. So these are the 3 combinations, and the question is, why is the sum of these terms 0? Well, first of all, you can push this one to the middle by means of that identity here, or something similar to that identity. So you act on a central vertex, and here what you do is you sort of invent a propagator. You say delta, you use the Green's identity. You say propagator times the equation of motion is a delta function, and since this is a delta function which forces this vertex to the outside, you can insert this quadratic part of the action, which is the equation of motion, times the propagator, and then you get this. But the nice thing is that now all of these things act on a central vertex, and the point is that this is just the cubic invariant statement of the action, and then that's 0. Now we can do the same for the Yangian symmetry, and then we get different types of terms. Again, some nonlinear local terms, some bilocal term here, and some bilocal term where you have nonlinear contributions. Again, you shift these things to the middle, and then you get this combination, and that combination is precisely the cubic invariance of the action. So again, that's 0 by means of what I've shown you in the first part of the talk. And we've also shown, we've also shown that this works if you do gauge fixing properly. But we can't really. I mean, this produces of the order of 50 terms, and I don't want to show you those. Let me just continue with the last 2 examples for the 4-point function. Again, you act with bilocal terms on the external legs or on the quartic vertex, and then there are different contributions for the nonlinear terms. And the point is you can shift everything to the middle, and again, by invariance of the propagator, 3 vertex and 4 vertex, and also by Yangian invariance of the 3 and 4 vertex, and by the commutativity of constituents, which is a funny coincidence, n equals 4 sup Yang-Mills, you do get 0. Finally, the 3-point function at 1 loop. So you get a whole lot of terms just by spelling out what this means. These are all the terms that contribute. And again, modulo gauge fixing and divergences. Well, modulo gauge fixing, you can show that all of these terms cancel as diagrams. The point, however, is that if you are careful, you should acknowledge the fact that you get divergences in these loop integrals. For example, these loop integrals will typically be divergence, and you should regularize first and renormalize, and that, of course may screw up this calculation big time. So the question will then be, can there be anomalies? Can the classical symmetries suffer from quantum anomalies? Problem here is we don't really know how to formulate anomalies for such non-local symmetries. It's not really a non-local symmetry, it's more non-local symmetry in color space, but not in space-time. We don't really know, we couldn't really formulate it as a violation of a non-local current because we don't know how to formulate the current for such a symmetry. But maybe there is some cohomological origin that you can use to formulate the anomaly. This anomaly consideration would again be similar to the anomaly consideration at the classical level that I showed you earlier. But here you should be a bit more careful in considering regularization, considering gauge fixing. Our belief is that there will be no anomalies because this integrability of n equals 4 super Yang-Mills does not only work classically, it works at the one loop level, it works at higher loops. So, and the Wilson loop expectation value works at one loop. So perhaps there's no anomaly to be expected. But of course this should be done carefully if you want to make a proof. So, okay, what I've shown you in this talk is that that you have Yangian symmetry in planar n equals 4 super Yang-Mills for the classical action, and in that sense the model is classically integrable, and we have done the same analysis for this n equals 6 Chern-Simons theory in 3 dimensions. So there are other models where this applies. This part of the talk I've skipped, but then I've shown you that due to this invariance of the action, you get certain Ward, Takahashi, or Slavnov-Taylor type identities, and these we've tested by looking at particular correlation functions with a few external legs. And of course, you should consider quantum anomalies. We don't expect them, but it would be good to show more rigorously that you cannot have such quantum anomalies. And then, of course, you can try to apply it to different objects like scattering amplitudes, Wilson loops, and maybe also derive some of the algebraic integrability methods through the existence of this Yangian symmetry. So connected to whatever methods have been constructed for addressing integrability and computing observables efficiently. Those should, in principle, you should be able now to relate this to this Yangian symmetry of the model. Thank you.